She studied here in La Laguna. She did her master's thesis also in La Laguna, and she did her PhD thesis with Jesus and Nacho Martin. And now she's about to finish, right? In May, she's defending her thesis and moving on onto the first postdoctoral position in a great city in Firenze, enough fellowship in Observatory of Arcetri, right? Yes. So, okay, so please go ahead. The floor is yours.
Okay. Thank you, Jorge, for the introduction. Also, thanks the organizers for inviting me to give this seminar. So what I'm going to present today are results that I found during my PhD thesis. So I work in the field of galaxy formation. And the main question that we wanted to answer during this thesis is whether dark matter halos and their properties can influence observed properties of galaxies that we observe in the local universe. So I'm going to start with introduction to the field. Okay, so when we observe galaxies in the local universe, we see a vast variety of types, shapes, sizes, and colors. So like the ones I'm showing here. So you see how these galaxies have redder colors, tend to have more spheroidal morphologies. As we go down, these galaxies are bluer, tend to have spiral arms. So in this sense, we see how there's a lot of different galaxies in the universe. And when we look at them in well-known diagrams, for example, the color stellar mass diagram, we also see that we tend to see a galaxy bimodality. So in this sense, redder and more spheroidal galaxies tend to have redder colors and cluster in this, for example, this what we call the red sequence passive galaxies, while bluer galaxies are in this blue cloud. So in this sense, we see this galaxy modality, for example, in this color stellar mass plane. This is also something that we see in star formation rates, and we measure the level of star formation in the galaxies. We see now how these star-forming galaxies, bluer, with a more active level of star formation cluster in the what we call star-forming main sequence, while these quiescent or passive galaxies that are not actively forming stars are below this sequence. So we tend to see how these galaxies tend to populate different regions in these diagrams. And for example, here you see how as we increase the stellar mass, we tend to have redder galaxies. For example, if we look at the stellar mass function, so at the number density of galaxies in a given region of the universe, if you see first this black line, you see how this number density of galaxies as a function of stellar mass, you see how this galaxy stellar mass function is dominated by low mass galaxies, and when we increase the stellar mass, this function goes down. And when we further separate the galaxies into star forming or passive or quiescent, we observe how these blue or star forming galaxies dominate the low mass end of the galaxy stellar mass function, while more massive galaxies are dominated by quiescent or passive galaxies. And in the bottom panel, you see how as we increase the stellar mass, we also increase the quiescent fraction in the galaxy population. When we look into stellar population properties, we see, for example, the metallicity or the ages, mean ages of the stellar population. So this is the average of a galaxy. This would be the average metallicity. So metallicity would be the amount of metals heavier than hydrogen that are present in the populations of the galaxies. So if we see that as galaxies are more massive, we see that they also are more metal rich and they are also older. If we instead of stellar mass, we look at the stellar velocity dispersion, we even see an even stronger correlation. So in this sense, we also see a dependence of the stellar populations on stellar mass. When we look at the star formation histories, so this would be the specific star formation rate, so star formation rate divided by stellar mass as a function of look back time. This would be earlier times, it would be redshift 0. What we see if we separate the galaxies into different masses, for example, if you see these galaxies red over here, the ones are plotted with red colors. So you see how they have a very high peak of star formation at earlier times. That is also very short in time. If we go to more massive, less massive galaxies, sorry, you see how this peak is more extended and later in time. And for example, these lower mass galaxies have a very extended star formation history. So they also see a dependence of the star formation histories on stellar mass. So what I wanted to show you with all these different plots and figures was that if we look at galaxies in the nearby universe, we tend to see that they follow well-defined scaling relations with baryonic properties. So in this sense, if we know the stellar mass of a galaxy, we kind of already know which properties this galaxy will have. But what about halo properties? So in our lambda CDM cosmology, galaxies do not grow and evolve in isolation, but they do so within dark matter halos. These halos are very vast and very massive and extend to much larger distances than the visible matter that we see in their center, so the stars and their gas. And these halos are embedded, as you see here, in a cosmic web-like structure that is composed by filaments, nodes, and underdense regions called voids. So the assembly of these dark matter halos is quite well and broadly understood theoretically, thanks to large n-body simulations that only have dark matter and gravity. So basically, simulation initially we have the initial condition of the universe, we let it evolve with only dark matter and gravity, and we end up with this large scale structure and these dark matter halos that are able to reproduce the large structure of the universe portrayed by large spectroscopic surveys. But of course, if we want to understand galaxies, we cannot only have dark matter and only dark matter halos. So in the centers of these halos, as I was saying, we have galaxies, and the scales that we are measuring are very different. So these halos are in megaparsec scales, galaxies, the visible components, around kiloparsec scales. Then within these galaxies, we have a complex variety of baryonic physics that is highly nonlinear and complex. So in a simplistic way, when cool gas is able to fall in these dark matter halos and is able to cool down, it can lead to star formation that happen in parsec scales. In the centers of these galaxies, there are supermassive black holes that inject vast amounts of energies into the galaxies and can affect their properties. And so in general, we need to also have a very good knowledge about baryons in order to understand galaxies. But what this thesis is about is that we cannot only just understand halo assembly in one side and baryonic physics in another side, because there's the baryonic physics of galaxies is coupled to the assembly of their host dark matter halos in which they reside. So in this, at the moment, it is a topic that is highly debated, and we don't know exactly how the coevolution between galaxies and halos over cosmic time can affect present-day galaxy properties. So a common way to study the connection between galaxies and halos is through the stellar to halo mass relation. So this relation is quite interesting because it shows us the efficiency of halos of forming stars. So if galaxy mass just scaled with the halo mass, we would see a constant relation that is actually not what we observe today. We observe this U shape that is very characteristic, and it's found by very many different works and techniques. And actually, baryons are the ones who are regulating the galaxy formation process in this low and high halo mass regime. As for example, there's a wide consensus in the field indicating that supernovae feedback is responsible for preventing star formation in these low mass halos, while in the case of high mass halos, we believe that it's a black hole feedback or AGN feedback, the one responsible to inject energy into the halos and prevent star formation. But if you see, the halo mass is the x-axis of this relation. So we are seeing that if we know the halo mass in which a galaxy lives, we already know as well which baryonic physics are going to be more or less efficient to drive the galaxy formation process. Okay. So for the rest of the talk, I'm going to focus on the high mass end of this relation. So and in addition to that, this relation has some scattering. So now I'm plotting stellar mass as a function of halo mass before we had the variety of stellar and halo mass. That's why we saw a U shape. So in this case, we have stellar mass as a function of halo mass, and this relation has some scatter. So in the sense that if for a given halo mass, we can have galaxies of different masses. So in this sense, the scatter is related to the efficiency of galaxy formation for a given halo mass. But as well, we also see that for a fixed stellar mass, we also see that galaxies can be in halos of different masses. So in our work, what we ask ourselves if its halo mass can influence present day galaxy properties. So it can affect, in particular, stellar population properties of galaxies. So to answer this question, we turned to the Sloan Digital Sky Survey. So we selected a central galaxy. So central galaxies, because sorry, I had it in the slide, but I didn't mention all this. This stellar to halo mass relation is for central galaxies only. Central galaxies are the galaxies that are in the center of potential of the potential well of the dark matter halo, and typically they are the most luminous or most massive galaxy in the group or cluster. So we are focusing on central galaxies only, and of all galaxy types. And for SDSS, we have integrated optical absorption spectra. So we analyze these optical spectra with a full spectral fitting algorithm fed with a set of single star population models. So in a nutshell, what we did was so PPXF, this full spectral fitting algorithm, what it does is to find the best combination of single star population models that have a single age and a single metallicity that are able to reproduce the spectra that we observe. So in this sense, with this method, we can derive average ages for the galaxies, average metallicities, star formation histories, as I will explain later, stellar masses, and the velocity dispersion of the galaxies. And we combine these stellar population measurements with halo mass estimations from the group and cluster catalog. So basically, we selected central galaxies that are in groups or clusters with more than 3 members in order to have more reliable halo mass estimations. We compare in our work halo masses coming from different group and cluster catalogs based on different methods. But the ones I'm going to show here are the ones obtained with a variation of the abundance matching ansatz, which basically what this does is to rank the luminosity or the mass of a given group or halo and match it with a dark matter only simulation. So in this sense, these halo masses are obtained in an indirect manner. So what we did next was to color code the stellar to halo mass relation with the stellar population property. So I'm first, I wanted to say that these are ages and metallicities, but this with PPXF, but it's in agreement with a model-free approach, just measuring the line strength of the indices. So, okay, we're going to focus to one plot at a time. So here we have stellar mass as a function of halo mass color-coded by age. And what did we find? So you see how these galaxies over here are older, these galaxies over here are younger. So when we fix the halo mass of the galaxies, we recover well-known correlation of the stellar population parameters, and we see how more massive galaxies are older, less massive galaxies younger. What is more interesting is that if we fix the stellar masses of the galaxies of the same stellar mass, if they reside in halos of different masses, they have different stellar populations. This is quantified in the paper through a partial correlation analysis, which is shown here in the bottom, in this corner. And basically, this red arrow, what it does is to indicate the maximal increase of the stellar population parameters. So in this sense, we see that if this line was vertical, it would mean that they would only depend on stellar mass. That is something that we know. But we also find this secondary dependence with halo mass. This is also something that we see in the metallicities of the galaxies. So you see a very similar behavior that what we found in age. So in this sense, this would be more metal rich, more metal poor. More massive galaxies are more metal rich, less massive galaxies are more metal poor, but when they live in halos of different masses, they also have different metallicities. And you may be wondering, what about velocity dispersions? Because we also know that stellar populations also correlate very strongly and even more tightly with velocity dispersion than with stellar mass. I'm sorry, this is what I was saying earlier. And so what we did is that we changed the y-axis of this relation. So now instead of stellar mass, we have the stellar velocity dispersion of the galaxies as a function of halo mass. And we even see now, we recover again galaxies with higher velocity. Sorry, I was pointing my up. So galaxies with higher velocity dispersion are older, are also more metal rich. Again, these panels are analogous to what I showed you before, but now with velocity dispersion here. So when we did the partial correlation analysis, now we even see a stronger correlation that is indicated with this black line at fixed halo mass with the velocity dispersion. But again, even though that this correlates strongly with velocity dispersion, we still see a secondary dependence on halo mass once we account for this dependence on velocity. So we find that velocity dispersion is a better predictor of the star populations than stellar mass, but again, we also see this secondary behavior of halo mass driving the galaxy stellar populations. Okay, and as I was telling you earlier, we can also derive with our method a star formation history. So the next step that we asked ourselves was if halo mass could also influence the star formation histories of the galaxies. So going back to the method, as I told you earlier, with PPXF or full spectral fitting in general, finds in this case the best combination, the best linear combination of single stellar population models that best reproduce the galaxy spectra. So here you for example, see a grid of single stellar population models of metallicity and age. And what PPXF does is to assign weights to the models in order to reproduce the spectra. So in this sense, you see how in this case, this galaxy is very metal rich and also very old. So we can translate these weights into flux fractions. So we can know this flux fraction associated to models of different ages. We can translate that into mass fractions with mass to light radius. And we know the time difference between the models, so we can know the mass form at different times, which is star formation history. So this method has its own caveats and limitation, and for example, it inherits the limitation from the SSP models, but still it's able to recover the overall shapes of the star formation histories. So what we did is now star formation histories are in 2D, so we cannot just color code the relation. So what we did is to bin the stellar to halo mass relation in different stellar mass bins to see if they also are influenced by the halo masses of the galaxies. So here I'm showing you the cumulative mass fraction as a function of lookback time. So again, this would be earlier times. This would be redshift 0. And these curves, when they reach 1, they reach the present day mass, stellar mass of the galaxy. So what we did is to divide the galaxies in halos of different masses. And you can clearly see that they have different cumulative mass distribution. So what we see here is that at fixed stellar mass, this darker color would be halos of the lower masses, intermediate masses, higher masses. So you see how in these halos form their stars faster and more rapidly, and these halos do it more slowly. And these lines, these vertical lines, indicate the time in which these halos form 95% of their present stellar mass. And you see how these halos, galaxies in these halos, sorry, do it earlier than these galaxies in more massive halos that do it later. And this is in very well agreement. So I'm pointing at this again with the star to halo mass relation. So you see how galaxies over here, so at fixed stellar mass and in more massive halos, and they also have more extended star formation histories. And these galaxies that are older have form the stars or the bulk of the stars earlier on and over shorter timescales. So when we look now at the star formation rate as a function of look back time, it's another way to look into the growth over cosmic time. You see that now these galaxies in these low mass halos have a very high peak of star formation rate at earlier times. They decline the star formation rate with time very rapidly, maintaining very low levels of star formation rate today. In contrast to galaxies in more massive halos, which have a lower peak at earlier times, decline their star formation not so rapidly, and even they rejuvenate and have higher levels of star formation rate today. So this is in a stellar mass bin. When we go to so basically now we increase the stellar mass in these bins, we see that the behavior is the same, but it's kind of diluted, and even in these high mass bins, we kind of don't see a difference. So it makes sense. So because as we go up in stellar mass in this plane, you see how everything in this high stellar mass and halo mass regime, everything tends to be older, more metal rich, and so we don't see a difference in the star formation histories. So in this sense, it's consistent to what we found for the stellar population properties. So we find that the scatter of the star to halo mass relation correlates with galaxy ages and metallicities, and especially in the low halo mass regime. And we also see that galaxies in different mass halos have also different star populations and star formation histories. I'm gonna make a very quick parenthesis. So in this latest work in which we had the star formation of the galaxies, we also studied the origin of the star forming sequence, the relation that I showed you at the beginning. So we found, so very quickly, if you're interested in this, please talk to me later and contact me. But basically, we find that the relative position of the galaxies with respect to the main sequence indicates as well that it's connected to the star formation histories of the galaxy. So in this sense, these galaxies over here in the upper main sequence at fixed stellar mass have experienced more prolonged star formation histories than passive quiescent galaxies. So if you're interested in this, please talk to me later. Coming back to the star to halo mass relation. So when we compare these results with other works in the literature, we find that there's quite a lot of debate in the field. So while we find, and other works find, that at fixed halo mass, more massive galaxies tend to be older, redder, or passive, others find that they tend to be younger, bluer, and star forming. And this, in principle, they suggest opposite results. But there's quite a lot of discrepancy in the field because of mainly these different reasons. So this is more of a technicality. So again, if you want to ask me later, please do so. But all these different works use, as I'm with this second point, and analyzing the star to halo mass relation in observation with many different ways, not only measuring halo masses in different ways, but also analyzing the data in different ways. And in this case of simulation, the case is also not trivial, because the way in which you implement the baryonic physics in your hydro simulations, for example, can affect how the scatter of the star to halo mass relation is connected to galaxy properties. And even though there are works that invert the relation, so instead of stellar mass as a function of halo mass, you have halo mass as a function of stellar mass. And then if you further divide the galaxies into star forming and quiescent, and also bring the galaxies according to the x-axis of the relation, which is different, galaxies can have different statistics in this plane, so it can lead to misleading results. So please, when you compare different works, please be careful about what are the relation that these works are studying. So in our case, we are using this 2D plane, and we are not binning the galaxy, not separating the galaxies into different categories. So we are safe, but it's true that our halo masses, as I'm showing here, are estimated in an indirect way. And at the moment, there is currently no large galaxy samples with halo masses for individual galaxies, measured, for example, with galaxy rotation curves. So in our next work, we ask ourselves if we could do better and if we could find an alternative and direct observational evidence of the role of dark matter halos influencing observed properties of galaxies. So, wait, so a second. And for that, we turn to the CALIFA survey. So CALIFA is an integral field spectroscopic survey whose main aim was to provide a spatially resolved view of the local universe. So in this work, we are focusing on 300 galaxies of CALIFA that were observed with a high resolution configuration in order to derive high quality stellar kinematics. And why are these high quality stellar kinematics interesting? Is because they allow us to derive detailed Jeans dynamical modeling. So what this dynamical modeling does basically is to fit the stellar dynamics, assuming a dark matter potential, So they allow to derive the total masses enclosed within a given aperture. So these total masses are a dynamical tracer of the stellar motions, and not only incorporate a stellar component, but also a dark matter component. And with CALIFA, we can go up to 3 effective radii, which is quite a large extent. So what we did in this work is propose this new relation, is stellar to total dynamical mass relation. So here we have stellar mass as a function of total dynamical mass. And these total dynamical masses are completely independent of this y-axis of the relation, which are obtained in this case with SED fitting. So what we did again was to color code now the stellar to total dynamical mass relation with galaxy ages, and on the left, galaxy metallicities on the right. You see, again, the ages and metallicities are measured within 1 RE with the starlight code fed with the Miles and Granada models. And this is described in detail in González Delgado 2015. Okay. So we see now how galaxies over here are older, are also more metal rich. These galaxies in this lower regime are younger, and they also tend to be more metal poor. We did again a very similar analysis to quantify the dependence or the partial correlations with the data. And we find again that if we show here this black line would be the partial correlation of age and stellar mass if we fix the total mass of the galaxies, and we see that both age and metallicity correlate with stellar mass at fixed total mass. But again, we find as well a secondary dependence on the total dynamical mass measured within 3 effective radius. So in this sense, at fixed stellar mass, these galaxies also show a dependence. At fixed stellar mass, the stellar population properties, so ages and metallicities, show a dependence on the total masses. So, and this again, the red line indicates the maximal increase of these stellar populations in these planes. So what I'm saying here? So stellar mass alone is not able to capture the behavior of the stellar populations, but we need a dynamical tracer sensitive to the stellar motions that incorporates both a stellar and a dark matter component to be able to reproduce the behavior of the star populations. This is not, this is not something that we only see in the Galaxy stellar populations, but if we go to further observables, here we have stellar angular momentum, star formation rate, morphology, that's what they for their Hubble type. So now we have galaxies that are more dispersion dominated, have lower star formation rates, and earlier type morphologies in this upper part of the relation. And galaxies over here, more rotationally supported, have higher star formation rates and later type morphologies. So in this sense, and when we compute again partial correlations, we see how all these properties increase in this way. So galaxy ages, metallicities, stellar angular momentum, star formation rate, and morphology are all behaving the same way in this plane. And even there's a work by William Baker and Roberto Maiolino, in which they analyze spiral galaxies on manga, and they look at gas phase metallicities. So this is inverted, this dynamical mass and stellar mass, but you see this black arrow would be your red line in our planes. You see how these galaxies show both a dependence on dynamical mass and stellar mass, so, for the gas phase metallicities. And I should note that the dependence that they found is weaker than the one we found because these dynamical masses are measured within only one array. Okay, so we have seen that a lot of different observables of the galaxy baryonic cycle are behaving in different ways. So, and for example, while we're measuring star formation rates or gas phase metallicities, we are sensitive to processes that are happening now in the galaxies, while morphology or the the angular momentum of the galaxies is set earlier on in their evolution. So, okay. Another thing that we found is that if you remember what I showed you for SDSS, and this is now what we found for CALIFA. These are two different relations. This is stellar to total dynamical mass relation, and this is a stellar to halo mass relation. And we are finding a very similar behavior of galaxy ages and metallicities in both planes. And not only that, so if we compare total dynamical masses and halo masses. So these halo masses are from the group and cluster catalog from Young, and you should focus now at the blue stars, which is CALIFA. So once we remove the dependence on stellar mass, both of halo mass and total mass, we see that those two parameters still correlate strongly with each other. And again, not only that, when we check the correlation between halo masses and total, oh no, perdón. A ver, perdón. A ver. Sorry. A ver si todavía funciona. Sí, perdón. Sorry. Okay, so I was saying that in Eagle, in the hydrodynamical simulation Eagle, when we compare halo masses, which in the simulation is of course trivial to obtain, halo masses are in this case M200, total masses is the sum of all the particles within a given aperture. In the galaxies, in this case, we took 20 kiloparsecs because that was the median of 3 effective radii for a galaxy sample. We see again how these halo masses and these total masses correlate as well in the simulation. And they also do have a very similar behavior in CALIFA and in Eagle. Okay. So in this sense, with total dynamical mass, it seems that we are tracing the behavior of halo mass at these scales. Okay, and what are the physical origin of the trends that we found? What could be causing that all of these different observables behave in the same way and have this dependence on total dynamical mass? So if we turn into simulations, now I'm showing you here the stellar to halo mass relation in a wide variety of simulations, this Eagle, Illustris, illustrious TNG, and different semi-analytical models. All these models show a dependence with halo formation time. So the scatter of the star to halo mass relation correlates with the formation times of the halos in all these different theoretical models. In addition, when the halo forms half of its current mass. So if you did it earlier or later. Dark matter mass. Yes. Okay. So, and for example, for the Eagle model, they also did an experiment that's genetically modifying the halo. So if we have a halo mass today of a given mass, what happens is you essentially shift their assembly history earlier or later. What happens is that you can change its present day properties. So this is the organic. So this was a galaxy that is high okay level star formations, little bit of star parallels. What happens if you shift the assembly history of the halo earlier? So you end up with a spheroidal system that have a low level of star formation and lower gas fractions today. If it contrary, you shift the assembly history of the halo later, you end up with a rotating disk, with a spheroidal morphology, higher star formation rates, and higher gas fractions. So essentially, just by shifting the formation time of the halo, keeping the whole galaxy formation model the same, and keeping the same halo mass today, you end up with a completely different galaxy at present day. And we also observe that the scatter of the star, I remind you what I showed you earlier in the previous slide, at fixed halo mass, earlier formed halos host more massive galaxies than later formed halos. So this could naturally explain our findings if we assume, or if we speculate, we hypothesize that these galaxies, these older galaxies over here, are older, are more metal rich, have lower levels of star formation, earlier type morphologies, and are dispersion dominated, while these galaxies are younger, more metal poor, have higher star formation rate, later type morphologies, and are more rotationally supported. And also, when we look at the star formation histories in the second paper with SDSS, we found that more massive galaxies also assemble the bulk of the stars earlier on in their evolution and faster, while while less massive galaxies did so over a more prolonged period of time. So, and even going further, we also know that the cosmic web, so in this sense, the position of the galaxies with respect to the cosmic web, so if the galaxies reside in filaments, if they reside in nodes or in voids, can affect galaxy properties and even galaxy star formation history. So it has been shown that galaxies that, for example, reside in voids, assemble the stars slowly or in a more extended period of time, that if than in contrast to galaxies that do it in more dense regions called sorry. So in this sense, this is an open question, and it's something that we have not investigated yet, but can the cosmic web affect halo assembly? So in this way, because it also has been shown that the cosmic web can also affect halo growth with halos that are in denser regions, also having, for example, earlier assembly histories. So can the cosmic web affect halo assembly, and then halo assembly is affecting the properties of galaxies? So this is something that we don't know, but it's something that we would like to work in the future. So with that, I get to my final slide. So we have found that our results indicate a connection between the baryonic properties of nearby galaxies and their host dark matter halos, in particular the mass of their host dark matter halos. we found that velocity dispersion seems to be the main driver of galaxy star population properties. But that they also have a secondary dependence on the halo masses of the galaxies. So, and not only average stellar populations show a dependence on halo mass, but also their star formation histories. So in this sense, halo mass seems to have a secondary role in driving the galaxy formation process. When we look at the star to total dynamical mass relation, we also find a very similar behavior that the one we found in the star to halo mass relation for baryonic properties, which also show a dependence on total dynamical mass. And we also find that total dynamical mass correlates with halo masses from group and cluster catalogs, and in cosmological simulations, total masses also correlates with halo masses from the atypical aperture of our galaxy sample. 3 effective radio of galaxy sample. I didn't show this, but if you want to ask me, please do so. But present day star formation rates in the star forming main sequence, when we are looking at the star forming main sequence, seem to have or retain information about their evolutionary paths. And finally, what I show you now is that we hypothesize that our results are driven by halo evolution, with galaxies and halos at different evolutionary stages in the stellar to halo mass relation, or in the stellar total dynamical mass relation. In this sense, these galaxies and halos being in different evolutionary stages would be driving the observed trends that we see today for all of these observables. Okay, so with that, thank you, and I finish. And I'm happy to take questions.
Okay, Laura, thank you very much for the very nice talk. Questions, comments?
Thank you for the very nice talk.
Yeah.
In reality, just a clarification.
Yes.
And you said it at the beginning, but it's still not very clear to me.
Yes.
When you were referring to halo masses,
Yes.
that are not dynamically determined.
Yes.
How were you calculating that?
Yeah, we don't calculate them. So we take them from group and cluster catalog. So in the paper, so the results I show you here are from the Young 2007 catalog. So again, what they do so is they rank the luminosities or the masses of the groups and clusters. So basically you compute the membership of galaxies to groups and clusters. You have the total luminosity or total mass, and then you compare that with a dark matter only simulation, and you basically populate that, matching the luminosity or the mass, and with that of the basically more massive galaxy to more massive halo, blah, 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 blah. Could be more massive cluster in this case. So it's an indirect measurement.
So naturally, you would expect that galaxies with larger stellar masses would be living in
so the
halos,
of course,
by definition,
of course,
construction.
Yes, of course, but that's why, because you could do this with isolated galaxies. So we did this with the galaxies that are in groups with more than 3 members. So in this sense, for the computation of the luminosity or the mass, we have accounted they have accounted for the luminosity or stellar mass of the groups. So in this sense, no, it's not just the mass of the central galaxy correlating with the halo mass, but we also have into account the ones of the satellites in those groups. It's an indirect measurement, of course.
No, I'm just trying to understand whether this already can imprint some of the relations that you are seeing because of the way galaxies are placed in the 2D location in the diagrams of stellar mass and halo mass. This was a little bit what I had in mind. Yeah, so of course, like what I can say again is like if you were having only isolated galaxies, you would expect, of course, a 1-to-1 relation stellar mass and halo mass, as they are taking into account the groups and clusters. These halo masses again are still indirect, but we also checked, for example, with group and cluster catalogs, that instead of abundance matching, they do calculate the halo masses with the dynamics of the satellites. Assuming the virial theorem. So, and we find, like, again,
like a very similar behavior that what I'm showing here with Young. And it's in the paper. I can show you. But it's so the idea is like these halo masses from group and cluster catalogs, from weak lensing, and all these different methods have a lot of caveats and a lot of limitations. So the idea is to try to explore as much proxies that we have of halo mass and see if we find consistent behaviors amongst all of them. And at least with these different, we tried in the paper for different halo mass estimations and from group and cluster catalogs, and they all behave in the same way that what I'm showing here.
Okay, thank you.
Yeah, thank you, Laura. If I understood properly, you focus on centrals.
Yes.
And so your main conclusion is that assembly bias is causing these trends. So if
Yes.
that's true, you should see a completely different behavior for satellites because they are not affected by the same assembly bias.
Yes.
Is this something that you looked into?
I haven't, but yes, of course. So in this case, like the central galaxies, so the satellite galaxies would be affected by environmental processes within the halos that would be different in halos of different masses, but I would expect that this washouts a lot for satellite galaxies. So I don't know what I would expect, but I haven't checked satellites. All of this is for central galaxies. Yes.
Thank you very much for these very interesting results. I wasn't at your thesis, so for me, it's a good opportunity to learn about them. For a fixed halo mass, or how much scatter is there in the baryon mass? Or for a fixed baryon mass, how much scatter is there in the halo mass?
A few. Okay, I don't have the number in my mind. If it's, I think.
Well,
yeah, it also depends on whether it's like a general consensus that the stellar mass and halo mass both correlate together, but in different simulation, different works, halo mass is determined in different ways. The shape of the relation can change slightly, so I wouldn't say a number. So it would change depending on the method that you're using, basically.
okay, I was thinking about the observations rather than the models.
Okay, so I can go
because
back.
obviously
Okay.
there are always outliers in these graphs, and the spread and the outliers tell you quite a bit about dark matter. And so I think there's some interesting things you can learn.
Okay. No, I haven't looked at that.
Anyway, thanks.
Okay,
very
but
much.
thank you. Thank you. I
Anyway,
haven't looked at that.
thanks very
Guys.
much. The result is
Thank
very, very interesting.
Thank you.
More questions? Well, I have one for sure, very nice. So, how would you test this hypothesis of the correlation between what you are observing and the assembly history beyond what maybe
course.
Mark has?
So generally we cannot measure halo formation times, of course, but halo formation time correlates with concentration, the concentration of the dark matter halos. So for the future, if we are able to measure gas up to large enough distances, so we are probing for example, the concentrations of the halos, that could help us to understand if this is the case. Also, what I was showing you with the cosmic web, if we study this relation in the context of the cosmic web and see how it's how can it affected by it, it could also give us clues if it behaves in the same direction. But of course, yeah, currently I think it's generally inaccessible to have a halo formation time in observations. Yes.
Okay. Thank you, Laura. So we have two questions online.
Yes.
Maybe, I don't know who was first. Maybe let's start with Wei Wang Kui, please.
Hello, can you hear me?
Yep.
Okay, great. First, very nice talk. Thank you, Laura. So regarding one question, actually, I have it also for this figure. If you fixed the galaxy stellar mass, and you would see the more massive halos they are living in, the galaxy age is lower, right?
Yes.
They are younger.
Yes.
But if you go to the accretion history of cumulative mass fraction that you have a plot before, and showing that how does at the fixed stellar mass it evolves between 3 different halo mass, right?
Yes.
For example, this one. The top left panel, you would expect the more massive one, more massive halo the galaxy lives in, tend to have a lower curve, which should mean they are more they should be older, right? No?
Yeah. And they generally are. So in this sense, this is T50, sorry.
Okay.
So you tend to see here in stellar to halo mass relation above, I wouldn't say 10.6 in stellar mass. Everything tends to be kind of old and kind of old in general.
Okay.
So I wouldn't expect to see a difference between the star formation histories, like a very strong difference in this regime.
Okay.
Or at least not a significant difference.
I see. Okay. Okay. I see it. Yeah. Good. Thank you. Yeah.
Yeah.
Okay, thank you.
Thank you.
Then another question from Patricia Sanchez Blázquez, please. Can you, yes?
Yeah. Thank you, Laura, for the very nice talk. But yeah, my question is, if you have looked at the number of members in the group, no, or satellites, and if it has any relation with the halo mass at a given central stellar mass, no?
Yeah, I don't have it here, but we look at this in the first paper. And basically we divided the galaxies into centras that are in groups with less than 10 members and with the one with more than 10 members. And we find the very similar behavior. So in this sense, for centrals that have more satellites, we see how the scatter of the relation reduces, and we have less statistics, but we still see how more massive galaxies are older and more metal rich.
Okay, my question was not slightly different. I mean, I was wondering if because the one thing is the halo mass, and another thing is the number of satellites. No, you can have two halos with the same mass and different amount of satellites. No, and maybe this is correlated with the time, the formation time. No, if it's more realized or not. So my question was if it's if you plot here instead of, for example, the color, instead of plotting you plot the number of satellites, if you could find, or the number of satellites normalized to the halo mass, because otherwise you're not going to see anything. If you could see it's also some trend, I don't know.
I think it has been shown before, and of course it goes, but yeah, I would have to check. Yeah, we haven't done it, but I think it has been done.
Because it's another way maybe to test what you want the formation time of the halo. Without
but
I don't know. It's,
okay. If we can discuss it further if you want.
Actually, my questions were other, but they were, I mean, Josefina already asked, and we went. So I was wondering if that could be,
Okay, I will have to think about it anyway, but thank you.
Okay, thank you very much. I think it's time to close this session. So thank you, Laura, again. It was a great success.
Thank you.
And then please remember that we have the scientific coffee outside, so you are all welcome to join and have further discussion with Laura.